now we look at the case where an object is moving both horizontally and vertically. We've looked at each thing separately, but now there's the case that happens quite often where both things are going on. We call that projectile motion. So a projectile is anything that's in free fall. So there's gravity pulling on it. There's an acceleration in the negative y direction, but it also has some horizontal motion. Now we spent some time in lab looking at what happened in this, and we saw that the horizontal motion was separate from the vertical motion. The horizontal motion was motion at a constant velocity, whereas the vertical motion was the accelerated motion, and that acceleration is downwards. That's why the parabola was curved down, and the acceleration was negative 9.8 meters per second squared. But the question comes up, it's what if you had a bullet and you drop it from the same height, and then you fire an identical bullet horizontally? And what'll happen is we'll see that in class. We'll look at the result there so you can kind of make your prediction, and then we'll figure that out in class. So there's the special case. This is the easiest version of how we can solve a problem with projectile motion. There was something where we fire something purely horizontally, so all of the initial speed is in the x direction. I'll give it the subscript x. And the nice thing is we don't have to worry about initial velocity, final velocity horizontally because it's at a constant speed. So we launch it from some height h with an initial speed v sub x. Gravity just pulls in the vertical direction, so the horizontal speed, as we saw in lab, is constant. And so we can look at the vertical velocity, v is equal to v0 plus at. If we launch it purely horizontally, the initial velocity in the y direction is 0, and then the acceleration is in the negative direction. So the path will look somewhat like this, as we'll see in class as well. The horizontal motion just causes it to move further and further in the horizontal direction, but the vertical motion is the same. At any given time, it will fall the same amount. So it's identical to if you just drop the ball. And so that equation is just our equation 3. The change in vertical position is v0 plus 1/2 at squared, but the initial velocity in this case in the y direction is 0, and the acceleration is negative g, so this just simply becomes negative 1/2 gt squared. So it's just the same thing we've had for acceleration, like we did the problems with the accelerating motorcycle or a car or anything like that. So it drops by a height h to get to the ground. So if we're looking at the time it takes to get to the ground, we figure out, all right, our vertical displacement, it starts out at the top at a height h, it ends up at a height 0, so our displacement is negative 8, it's dropped by a height h, negative just being the direction. So if the negatives cancel and we can solve for the time ends up to fall from a height h will simply be square root of 2h over g. And that's a really good result to remember, that if something falls from that height or is launched horizontally from a height h, it's only going to take a specific amount of time t to hit the ground, and we can always solve for that. And if you notice, that doesn't depend on the horizontal velocity in any way. So the horizontal motion is a constant speed, so the delta x is pretty simple. It's just v0t plus 1/2 at squared. We saw that the acceleration in the horizontal direction is 0, so that equation simply becomes constant motion. So the displacement in the x direction is how fast it's going in the x direction multiplied by the time. So we can actually combine these two equations and get the idea that the horizontal motion just depends on how fast it's going and how high above the ground it was. How far it lands away depends on those two things. So the initial speed in the x direction multiplied by the square root of 2 times the height that it's launched from divided by the acceleration due to gravity. So as the projectile is going, it follows the horizontal motion, will follow whatever it had at the beginning. So you drop something out of a plane, ignoring air resistance, it will follow at the same speed as what it's dropped out of and just follow a parabolic path to the ground. Now we get to the trickier case, and we're going to spend some time on this. It's the idea if a projectile is launched at an angle, there it has both initial x velocity and initial y velocity. And you can just draw it as a triangle and find the horizontal component depends on cosine, the vertical component depends on sine. So the initial speed v0 is how fast it's launched, and theta is the angle that it's launched at. And I love that the book decided to use a champagne cork as the option there. I'm sure you guys have plenty of experience launching champagne corks at people. Hopefully not. But it shows that the initial velocity is broken into the horizontal and vertical direction. And if you look, the horizontal component of the motion, as we found before, is constant. So at any given point along here, the horizontal velocity is the same. But if you look as it rises, the vertical velocity decreases because it's slowing down, gravity's pulling it down. It gets to the highest point, and then at that highest point, what do you think the vertical velocity is? And then that vertical velocity keeps decreasing in the negative direction as it comes back down. So we can rewrite our equations. Our horizontal motion is just initial velocity cosine theta times t, so it's just constant velocity. If you remember, this is exactly what we got for our lab. When we looked at the horizontal motion, it was just constant velocity. It was just a line with a constant slope. And the vertical motion was a parabola. And when we launched something up at an angle, we had initially went up and then came back down. And the equation for that is v0 sine theta times t minus 1/2 gt squared. And so these aren't new equations, they're just special versions of our equations of motion. And so we'll look at how to use those together in class. One thing, if you're kicking at different angles, you're launching things at different angles, without air resistance, you kind of have a trade-off. You get a maximum value, and we'll see that in class, of 45 degrees. But if you do any of the complementary angles from 45 degrees, like 60 and 30, one's 15 degrees above, one's 15 degrees below 45 degrees, you'll end up ideally with the same range. It's just they won't go as high in the air. But in reality, with air resistance, you get the things shot at a certain distance give you because of air resistance, the horizontal velocity slows down a lot more, and so it starts to fall. So in launching a baseball, instead of 45 degrees being the ideal angle, it turns out it's closer to 35 degrees just because of the air resistance. And you can go through and solve that mathematically, but that takes a bit of calculus. So make sure you're ready with this for when we come to class.